To understand molecular orbital theory deeply, we will cover these topics in this video. Main postulates of molecular orbital theory. Difference between bonding molecular orbitals and anti-bonding molecular orbitals. What is bond order and how we can find it? How to check paramagnetic and diamagnetic behavior, and how to determine the energy order of molecular orbitals. First, let's start with the main postulates of molecular orbital theory. The first postulate says that atomic orbitals intermix to form molecular orbitals. For example, in the case of a hydrogen molecule, when its two atomic orbitals intermix with each other, they result in the formation of molecular orbitals, and we will discuss this in detail. According to the second postulate, the number of molecular orbitals formed will always be equal to the number of atomic orbitals that intermix. This means that if two atomic orbitals are involved in mixing, it will always form two molecular orbitals. According to the third postulate, only those atomic orbitals will intermix with each other that have comparable energies. This means that the 1s orbital will overlap with the 1s orbital of another atom, and similarly, the 2s orbital will overlap with the 2s orbital of another atom. It is not possible that the 1s orbital of one atom can overlap with the 2s orbital of another atom. Now, we will move towards bonding molecular orbitals and anti-bonding molecular orbitals. To understand this, we will draw the molecular orbital diagram of a hydrogen molecule. As we know, a hydrogen atom has one electron, and it is present in the 1s orbital. So it means that in order to form a bond, these atomic orbitals should intermix. Here, we can see that two atomic orbitals are taking part in mixing, so it means that two molecular orbitals will be obtained. But we need to keep in mind that half of the molecular orbitals will have lower energy than the parent atoms, and half will have higher energy than the parent atoms. So, it simply means that the two molecular orbitals which will be formed in this case, one will have lower energy, and the other one will have higher energy than the parent atom. Now, it's time to see what actually is the difference between bonding molecular orbitals and anti-bonding molecular orbitals. Keep in mind that molecular orbitals that have lower energy than their parent atomic orbitals will be called bonding molecular orbitals, and those having higher energy than their parent atomic orbitals will be anti-bonding molecular orbitals. We need to understand one more important point. Since anti-bonding molecular orbitals are higher in energy than bonding molecular orbitals, they will be denoted by placing a star on them. For example, sigma star and pi star. Bonding molecular orbitals, due to their lower energy, will be denoted without a star, and they will be called sigma and pi bonds. Now we need to understand how we should place electrons in molecular orbitals. Keep in mind we need to follow the rules of electronic configuration, such as Pauli's exclusion principle, Aufbau principle, and Hund's rule. For example, in the case of a hydrogen molecule, since there are a total of 2 electrons in the atomic orbitals of hydrogen, we need to place them in molecular orbitals. Both electrons will be placed in the sigma 1s orbital, which is actually a bonding molecular orbital, and no electron will be available for anti-bonding molecular orbitals. This happens due to the Aufbau principle, which states that electrons must be filled according to their increasing energy levels. So first, we need to complete the sigma 1s orbital, and both electrons will be filled in it. Now, we will discuss what bond order is and how we can find it. Actually, bond order refers to the total number of bonds formed between two atoms when their atomic orbitals overlap. We can find the bond order of any molecule with this formula. Bond order is equal to total number of electrons in bonding molecular orbitals subtracting total number of electrons in anti-bonding molecular orbitals and divided by 2. We can understand this with the example of a helium molecule. As we know, the atomic number of helium is 2, so its valence electrons will be present in the 1s orbital, and its electronic configuration will be 1s2. To draw its molecular orbital diagram, the 1s orbital of one helium atom should intermix with the 1s orbital of the other helium atom. According to the postulates, 2 molecular orbitals should be formed. One will have lower energy than the parent atom and will be called a bonding molecular orbital, while the other will have higher energy than the parent atom and will be called an anti-bonding molecular orbital. As we can see, there are a total of 4 electrons present in the atomic orbitals of helium. So now we need to place them in molecular orbitals. According to the rules, 2 electrons should be placed in the sigma 1s orbital, and 2 will be placed in the sigma star 1s orbital. Now, to find the bond order, we will apply the formula. As we can see, 2 electrons are present in bonding molecular orbitals, and 2 electrons are present in anti-bonding molecular orbitals. So it will be 2 subtraction 2 and divided by 2, and its answer will be equal to 0. This means that the bond order of helium is 0. From this, we can conclude that helium will never form a bond since its bond order is 0. You can also check this for a hydrogen molecule, and its bond order will be 1, which shows that hydrogen will always form one bond. Now, we will understand the difference between paramagnetic and diamagnetic behavior. We need to remember that if there is any unpaired electron present in molecular orbitals, then that molecule will always be paramagnetic in nature. But if all the electrons are paired and no unpaired electron is present in molecular orbitals, then we should say that it is diamagnetic in nature. To understand this deeply and also to understand the main concepts of molecular orbital theory, now we will take the example of a nitrogen molecule. As we know, the atomic number of nitrogen is 7. From the electronic configuration of nitrogen, we can see that in this case, first of all, the 2s orbital of the first nitrogen atom should overlap with the 2s orbital of the second nitrogen atom and will form 2 molecular orbitals of nitrogen. And as mentioned earlier, electrons will be placed in them. But here, we need to deeply understand how 2p orbitals will overlap and how electrons will be placed in them. First of all, remember that 3 2p orbitals of one nitrogen will overlap with 3 2p orbitals of the second nitrogen. It means that a total of 6 orbitals are intermixing in this case. So, according to the postulate, 6 molecular orbitals should be formed. But we need to understand that half will have lower energy and half will have higher energy than their parent orbitals. This means that out of 6 molecular orbitals, 3 will be bonding molecular orbitals, and 3 will be anti-bonding molecular orbitals. In the next step, we need to place electrons of 2p orbitals into molecular orbitals that are being formed in this case. As we can see, there are a total of 6 electrons present in atomic orbitals, so we have to place them in molecular orbitals. All these 6 electrons will be placed in bonding molecular orbitals, and no electron will go towards anti-bonding molecular orbitals. Now, if we move towards the bond order of this molecule, again, we need to apply the formula, which shows that there are 6 electrons in bonding molecular orbitals, and no electrons are present in anti-bonding molecular orbitals. So, it will be 6 subtracting 0 and divided by 2. And its answer will be 3. This shows that the bond order of nitrogen is 3, and it will form 3 bonds. Now, if we look at its magnetic behavior, as we can see, all electrons in molecular orbitals are paired, and no unpaired electrons are present here. So, we can say that nitrogen is diamagnetic in nature. Now we'll discuss how to write the relative energy order for molecular orbitals. Keep in mind that molecular orbitals formed are different in energy from each other. So, in order to assign them an energy order, we simply need to start writing their energy levels in ascending order. For example, in the case of hydrogen, as mentioned above, sigma 1s will have lower energy than sigma star 1s. Similarly, if a molecule also has 2 s orbitals involved in mixing, we can say that the energy of sigma 2s will be lower than sigma star 2s. But one thing we need to keep in mind is that the energy of pi squared py and 2pz will always be equal. So, by following this simple concept, we can write the energy order for any molecule. Now we will discuss how molecular orbital theory explains ions such as hydrogen ion, nitrogen ion, and oxygen ion. First, let's start with hydrogen ion. As we know, a neutral hydrogen atom has 1 electron in its 1s orbital. When 2 hydrogen atoms combine, their atomic orbitals intermix to form molecular orbitals, resulting in bonding and anti-bonding molecular orbitals. Now, if we consider hydrogen molecular ion, we can see that only 1 electron is available. According to the Aufbau principle, this electron will be placed in the lower energy bonding molecular orbital, which is sigma 1s. Since there is no electron present in the anti-bonding molecular orbital, which is sigma star 1s, the bond order can be found using the formula. So we can see bond order will be equal to 1 subtracting 0 and divided by 2, which will be equal to 0.5. Since the bond order is not 0, it means that hydrogen molecular ion is capable of existing as a weakly bonded species, but it will be less stable than hydrogen molecule. Now, let's move to nitrogen ion. For a neutral nitrogen molecule, we know that nitrogen has an atomic number of 7, meaning its electronic configuration is 1s2, 2s2, 2p3. Now, let's consider nitrogen ion. Since nitrogen negative ion has 1 extra electron, it will be placed in the next available molecular orbital, which is a pi star 2p orbital. Now, the bond order will also change. Bond order will be equal to 8 subtracting 3 and divided by 2, which will be equal to 2.5. This means means that when an extra electron is added, the bond order decreases, making nitrogen negative ion less stable than a neutral nitrogen molecule. Now, we will discuss oxygen ion, molecular orbital explanation for O negative ion. Now, if we consider oxygen negative ion, it has one extra electron, which will enter the pi star 2p orbital. This changes the bond order as follows. Bond order will be equal to 8 subtracting 5 and divided by 2, which will be equal to 1.5. This means that oxygen negative ion has a lower bond order than a neutral oxygen molecule, making it less stable and weaker in bonding strength. Effect of charge on bond order and stability. From these examples, we can conclude that adding an electron, as in nitrogen negative ion and oxygen negative ion, decreases bond order, making the molecule weaker. Removing an electron, as in hydrogen molecular ion, reduces bond order but does not completely eliminate bonding. More charge generally results in a weaker molecular bond due to increased electron repulsion in anti-bonding orbitals. Now moving towards limitations of molecular orbitals theory. It has several important limitations. Number 1. No clear molecular shape. It does not explain the exact shapes of molecules, unlike VSEPR theory. Number 2. Complex mathematical calculations. The theory relies on advanced math, making it difficult to apply. Number 3. Fails for some molecules. It does not correctly predict bonding in certain molecules, such as oxygen, where experimental results show differences in magnetic properties. Number 4. Weak explanation of bond strength. It does not always explain why some bonds are stronger or weaker in certain molecules. Number 5. Contradictions with other theories. It sometimes disagrees with valence bond theory, which explains bonding in a different way.